All right, let's talk about a shape you probably think you know, the parabola. But today, we're going to look past its familiar U-shaped curve to uncover the beautiful, precise geometric rule that actually brings it to life. So, I bet when you hear the word parabola, the first thing that pops into your head is just a U shape, right? Maybe you think about the path of a basketball heading for the hoop, or maybe the shape of a satellite dish. And that's a great start, but it's really only half the story. Because what if I told you that every single point on that perfect curve is placed there by an elegant, unchangeable rule? It's kind of like a secret code that dictates its exact form. And that is exactly what we're going to do today. We are going to crack that code. Let's reveal the fundamental principle that truly defines what a parabola is. Okay, here it is. This is the secret. A parabola isn't just a random shape, it's a collection of points. And every single one of those points has to follow one simple law. It must be the exact same distance from a special point called the focus as it is from a special line called the directrix. Equidistant, that's the magic word. That is the key to everything. Now, this one rule creates a whole cast of characters that give the parabola all of its unique properties. So let's meet the key players that make up its anatomy. First up, the vertex. This is the point you're probably most familiar with. It's the absolute bottom or the very top of the curve. You know, the point where the parabola stops going one way and starts heading back the other. Slicing right through that vertex is the axis of symmetry. Think of it like a perfect mirror. It's a line that splits the parabola into two identical mirrored halves. Everything on one side is a perfect reflection of everything on the other. And here's one of the real stars of the show, the focus. This is that special fixed point inside the curve, and its location is everything. The unique shape of the parabola means any energy, like a radio signal or light, that hits the inside of the curve gets reflected directly to this single point. That's literally how a satellite dish works. And it works in reverse too. If you put a light bulb at the focus, a car headlight can project a powerful, straight beam of light. Its location is absolutely crucial. And for every hero, there's a counterpart. Meet the directrix. This is the fixed line that stays outside the curve. And remember the rule? Pick any point on the parabola. Its distance to the focus is exactly the same as its distance straight to this line. They're always in perfect balance. Now for a fancier term, the latus rectum. It sounds way more complex than it is. It's just a line segment that passes through the focus, is parallel to the directrix, and touches the parabola on both ends. It's a Latin term that means straight side, and it gives us a really precise way to measure the parabola's width right at its most important point. Now, we can actually put a number on this whole relationship using a concept called eccentricity, which we label with an E. It's really just a ratio. You take the distance from a point to the focus, and you divide it by the distance from that same point to the directrix. This one single number tells us the exact type of curve we're dealing with. So if the defining rule for parabola is that those two distances are always equal, what does that make the ratio? Exactly. For every single parabola that has ever existed or ever will, the eccentricity is exactly 1. It's its unique fingerprint. No other shape has it. All right, that's enough theory. Let's see how this all works in practice. We're going to take a single equation and use our new knowledge to build a complete blueprint of its parabola, finding every single feature we just discussed. Here's our equation. Now, the first and most important step is to make it look like the standard formula. This format is the key that unlocks everything else. And lucky for us, our equation is already in this form, so we're ready to go. By comparing our equation to the standard form, we can just pull out 3 magic numbers, h, k, and p. In our case, h is 4, k is -1, and since that 12 in front is equal to 4p, a little division tells us that p must be 3. These 3 little numbers are about to tell us everything we need to know. Let's start with the easy one. The formula for the vertex is just hk. We just found h and k, so we plug them in, and there it is. Our vertex is at the point 4, -1. Simple as that. Next, the axis of symmetry. For this type of parabola, the formula is the vertical line x equals h. Since h is 4, our axis of symmetry is the line x equals 4. This is the line that perfectly cuts our parabola in half. Now for our all-important focus. Its location is given by the formula h, k plus p. We just plug in our 3 numbers. H is 4, k is -1, and p is 3. So, -1 plus 3 gives us 2. Our focus is right at the point 4, 2. And what about the directrix? Its formula is the line y equals k minus p. Again, we plug in our values. K is -1 and p is 3. So -1 minus 3 gives us -4. The directrix is the horizontal line y equals -4. And notice how the vertex at y equals -1 sits perfectly in between the focus at y equals 2 and the directrix at y equals -4. It all just fits. Finally, the latus rectum. We need its length and its endpoints. Now, the formulas on screen look a bit more involved, but don't worry. They're built from the same three magic numbers, h, k, and p, that we've been using all along. Let's calculate it. The length is the absolute value of 4p. Since p is 3, 4 times 3 gives us a length of 12. For the endpoints, we just plug our values into those formulas. This gives us our 2 points, -2 and 2, and 10 and 2. And check out that beautiful symmetry. Notice both endpoints have a y-coordinate of 2, meaning they line up perfectly with the focus. And just like that, we've done it. We've taken an abstract equation and turned it into a complete, detailed map of a parabola. Let's see it all together. Look at that. The whole shebang. The standard form, our 3 key parameters, the vertex, the axis of symmetry, the focus, the directrix, the latus rectum, and even the eccentricity, every single feature all unlocked from that one initial equation and the fundamental rules of what a parabola is. So we'll end with this. We discovered that a parabola is defined by a simple rule of equal distance, giving it an eccentricity of exactly 1. It makes you wonder, doesn't it? What happens when that ratio isn't 1? What secrets of shape and form are waiting to be unlocked inside circles and ellipses? That's something to think about. Thanks for joining me.